All right, we're trying to learn how to add vectors. We did a little bit of this in class. I'll just review real quick. We have one rule that says we can add two vectors if they lie along the same straight line. Here I've got an example of such a case, two vectors A and B that lie along the same straight line. Notice that in this case, I've got both vectors lying along a context line. These black lines are my context lines. They're the standard ones that you've seen in trigonometry and algebra before, a vertical line and a horizontal line. And I've defined which way is positive. All of that is negotiable. All of that is arbitrary. I don't have to define my context lines that way. Context lines are simply imaginary lines that help me define a direction. And in this case, I'm using the standard lines, and that allows me to use this symbol when I get an answer, because this symbol only applies when I have the standard context, horizontal and vertical lines, with positive to the right, positive up, and 0 degrees is to the right. Adding vectors, this is how I say I'm adding two vectors algebraically, with vector hats over each variable name, which tells me these are vectors. This means add these like vectors taking direction into account. That's what this symbolism means. But to crunch numbers, I need to make a scalar equation. Scalar equations have no hats over the top. These are just lengths of the vector. The directional information comes from using these rules. And in this rule, it says they add like scalars. So I put in a plus b, which is 5 plus 3 equals 8. Notice both a and b are pointing in the positive direction, so they show up as positive numbers in my equation and give me a positive 8. Simple example of the rule. Here's another example we looked at briefly in class. If b is pointing to the left, I have the same vector equation. I want to add a and b as vectors. This symbolism means take direction into account when you write the scalar equation. Here's the scalar equation. Now a is to the right, and therefore it's positive because that's my context, so it stays positive. B is to the left, which therefore must be negative. So the negative here is telling me that b is pointing to the left. Now I've taken direction into account in the scalar equation, and I get 5 minus 3 equals 2. And the length of the c vector is 2, but it's still pointing to the right because a is longer than b. So the net result is going to be still pointing to the right. Then we have two vectors adding together like Pythagoras. This is when I have the second rule of adding vectors. If I have two vectors that are perpendicular to each other, then I'm going to add them like Pythagoras. I've got a here to the right, b is down, they're perpendicular to each other. So the first thing I do when I have perpendicular vectors that I want to add together is I make a construction. I make a rectangle out of these two vectors. I draw a line from the tip of vector B, and I draw the line parallel to vector A. I draw a line from the tip of vector A parallel to vector B. Where they intersect, I draw a diagonal across the rectangle. That's C. There's an angle here which tells me the direction of C, because C is now not horizontal or vertical, so I have to give more information. How does C point? I don't know yet, so I'm going to call it theta, a variable. We had trigonometry that we put on the board the other day, where we have SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, SOHCAHTOA. The ratio of two sides gives me the sine or the cosine or the tangent. It just depends on what two sides I pick. Here are the sides in this case. Here's theta. This is the theta I've defined. So this side must be opposite theta. This side is adjacent theta. And this is the hypotenuse. Now that I've got my construction made, I can use the rule to add my two vectors like Pythagoras. C, as a scalar, is going to be a squared plus b squared square root. That's square root of 5 squared plus 3 squared. That's going to end up being 5.83. do that on your calculator. That's the length of the vector c. Now I want to do the calculation of the angle. So when I have two sides of a triangle, I can use those two sides to calculate a ratio, and then I can get the sine or the cosine or the tangent of the angle. When I have two sides of a triangle, and I do that, and I figure out this ratio, then I'm looking for the angle. I don't know the angle in this case, and so I'm going to use what's called inverse trig functions. They look like this: inverse sine of opposite theta over hypotenuse equals theta. Inverse cosine of adjacent to theta over hypotenuse equals theta. And inverse tangent of opposite theta over adjacent to theta equals theta. So I have three ways to figure out theta. Which one I use depends on what sides I know, what two sides I know. So if I know the opposite and the hypotenuse, I obviously want to use inverse sine. If I know the adjacent and the hypotenuse, I want to use inverse cosine. If I know opposite and adjacent, I want to use inverse tangent. If I know all three, I can use any one I want. So the idea here is we know all three. We know the adjacent is 5, we know the opposite is 3, and we know the hypotenuse is 5.83. But I'm going to avoid using the 5.83 because that's been rounded off. So in order to avoid round-off errors, I'm going to use the inverse tangent. So I'm going to get the inverse tangent of the opposite side, that was the 3, and the adjacent side, that was the 5. If that's not clear, go back in the recording and look at the diagram. And that equals theta. Let's pull up the calculator here. Here's my scientific calculator built into to Windows, and here's how you do it. You start by calculating this ratio. So I'm going to take this 0.6, and now I want the inverse tangent. Well, if I look here, that's sine, that's cosine, that's tangent. If I push this button right here, I get another set. I get inverse sine, inverse cosine, inverse tangent. I want inverse tangent. It tells me 30.96. So this equals 30.96
degrees. And here's an important point. Make sure your calculator is set to the degree mode, so you get the right answer. Okay.
All right, so now I can say that C in this case as a vector is 5.83 units long, angle minus 30.96 degrees, because it's clockwise from 0. It goes from, if I start at 0, if I start along this line, which is the 0 degree, I have to go clockwise 30.96 degrees. And in the standard format, that's a negative angle. So minus 30.96 degrees, right? If I'm going to use this symbol, I have to take that into account. If I want to just draw a triangle, I know that this angle here is 30.96. The distance in angle measure between these two lines is 30.96. Positive, negative doesn't make any difference at that point. The only reason I'm putting a negative in the angle right now is because I'm using this symbol, which means I have to use the standard trig definitions. This says clockwise rotation from the positive x or horizontal axis. Okay, so anyway, what we just did was we found the net vector by adding two vectors. If we had three vectors, we would pick two, add them together, then take that one and add it to the third. If we had four vectors, we'd take 2 by 2, add them together, and then take the results of those two, add them. And you always go 2 by 2. You can have as many vectors as you have. This technique does not mean you can't have 3 or 4 or more vectors. You can have many, 5, 6, 7. So you just do them 2 at a time. That's all, just 2 at a time. You pair them up, do 2, get the result, and then carry on from there. All right, so let's take a look at a case where we're not going to have either rule working for us. So let's make some context lines. So here's some context lines. Okay, so now let's take a vector, and we'll keep this one here. There's A again. Okay, that's vector A. And A still equals 5. And now we're going to do B, but we're going to do B a little bit differently. There's B. It is no longer along a context line. It is now off the axis lines. And I still represent it as B vector equaling 3. That's the length of the vector. I got to show more information so you can see the angle. So I'm going to put in more information. I'm going to put in, here is theta, and we're going to say theta equals, let's say that's 20 degrees. Okay, not plus, not minus. I don't care about rotation, counterclockwise, clockwise. Just the angle in between those two lines where I've got the arc shown is 20 degrees. And now we do our construction. Whenever we have off axis, we do a construction. We draw the dotted lines from the tip, parallel, and now we have, here's the part you need to understand. This is the tricky part here. I'm going to create 2 new vectors. This is by, and this is bx. They're both vectors. And here's what we're doing. We're working off of our previous result. Bx and by equal components of b. Vectors bx and by are components of b. Here's what I mean. Instead of thinking of this problem as adding vector a and adding vector b to get vector c, which is what I want, I look and I see that my two vectors of interest, a and b, do not follow either rule. Neither one of them is in the same line with each other. Neither one of them, they're not perpendicular to each other. And so I'm going to choose to take the off-axis vector b and I'm going to break it up into its components. And instead of thinking of vector b as this line that I've drawn initially, I'm going to think of b as the sum of bx and by, which is exactly what we just did. In the previous problem, I gave you two perpendicular vectors. We added them together and they came out to equal the perpendicular across a rectangle. Now we're just going in the opposite direction. I'm giving you a vector that I can create. I can make it into the diagonal of a rectangle by drawing the box. And then these sides of the rectangle are what I'm looking for, but it is true that those two added together give me back the vector that's the diagonal across the box. These two perpendicular vectors, bx and by, are the components of vector b. So I'm decomposing vector b into two perpendicular vectors. Why do I want to do that? It seems like I'm making my problem more complicated. I'm taking one vector and making two. I've now got three vectors to add together instead of two. That's true. I'm making some complexity, but I'm also making some simplification because look, what I've got now is vector bx is in straight line with vector a. I can add those two together. That looks like the second problem we did up above. And then look, by is perpendicular to these two. So I can use my other rule of adding vectors. So by breaking the off-axis vector b into components, bx and by, that are both on axis, I've now got a problem that is more tractable because I have things that follow my rules. So here's what we're going to do. We're going to say a bx as a vector equals vector a plus vector bx. I've made a new variable name, abx, right? It's going to be the sum of a and bx. You can see why I named it like I did. This is the vector equation. And I have now got to create the scalar equation. Let's make sure I've got my context correct. That's positive. That's positive. And so I now have a is 5. And now I've got to have minus bx. And I don't know how long bx is. I have no idea how long a bx is. I know what to do with it. If I knew what it was, I know I could put it in this equation and get what I'm looking for, but I don't know what it is. So here's where I use trigonometry. Here's my triangle, my right angle triangle. And I have opposite theta, adjacent to theta, and hypotenuse. Now notice I've got two names now for every line. For every vector has two names. by is also now being called adjacent to theta. The hypotenuse also is b, vector b. And the opposite theta is really the same as bx because this is a rectangle. And the opposite sides of rectangles are the same length. So these two are the same length. So bx is really the same as opposite theta. And the reason I rewrite the names is because now I remember the trig rules that I had, the SOHCAHTOA. So I'm trying to figure out bx. So I need a SOHCAHTOA. I need something with opposite theta in it. So let me take cosine. Cosine of theta equals, sine of theta. Opposite. Sine of theta is opposite theta over hypotenuse. And this is the opposite of theta is my bx, which is what I'm looking for, divided by the hypotenuse, which is 3. Well, this, if I rewrite it now, sine of theta, which is now really sine of 20 degrees, because theta is 20 degrees, equals bx over 3. There's a little algebra problem to solve. Just like we did the other day in the homework and on, prior lectures. If I multiply both sides by 3, I can say 3 times the sine of 20 degrees equals bx. Well, I can do that because I have my calculator. My calculator says I can take 20 degrees, take the sine of it, so turn this off, and now I get just sine here. Sine of 20 is that times 3 equals 1.03. We're going to round it to 1.03. 1.03. So bx is 1.03 long. So I'm going to go up and put that up here. So I keep this information, 1.03. I can put it in here and I can say equals 5 minus 1.03 equals 3.97. So ABX is 3.97, okay? And what's the direction? The direction of ABX, let's take a look. I've got two vectors that are horizontal and I'm adding them together. The longer vector is to the right, so clearly ABX is to the right. So let me just write that down. So this is going to be, I'm just going to put a little arrow here to say 3.97 to the right. Right? And then I'm going to, let me just kind of highlight this as a result that I'm interested in. That's ABX. Okay, 3.97 to the right. Okay, so I've got ABX. So now if I redraw my situation, let me make a copy here. Let me grab copy, paste, so I don't have to draw it all again. Now let's clean this up a little bit. Got too many things on here. So now that I've got
some stuff done, so let's see here. There we go. So ABX is now gone. ABX is gone. And now I have a vector
change the color of this here so we see that it's a different vector. Let's make this kind of a, well, we'll just make it blue. All right, so this is now ABX equals 3.97. That's how long that is. Okay, it should actually be a little shorter than the previous vector, so let me bring it back like that. Okay, there's ABX. All right, and now I have BY, and I'm going to drag this all down a little bit. I don't want that. Huh. All right, let's grab it another way. Huh. It wants to grab some of these other things. So we're just going to move this. I need to draw here. I need to get rid of these things. So let's see. Can I drag this down here? This BY. I need to draw another rectangle, and then I need to draw another vector, and let's make this orange. So here is vector C. And C is going to be ABX plus BY. C is also the same as A plus B, which is what I started out wanting to know. But what I've done now is I've created a new vector, ABX, and now I'm going to, instead of adding A and B, which was hard for me because they weren't in the same line with each other and they weren't perpendicular to each other, so they created a problem. I created a new vector, BX and BY, and now I'm using them to get to the final result, C. So we're breaking the problem up into more steps, but each step is easier because I have rules to follow. This is often the way it is in math. If I can't directly calculate something, then I do an end run and I try to come at it some different way. So now I've got the scalar equation is ABX plus BY, which equals, now ABX we know is 3.97, and BY I don't know, but look, take a look at the diagram. You always have to go back to the diagram. This is ABX, this is BY. They're perpendicular to each other. So I have to add like Pythagoras. So I have to square each of these and then take the square root. Then I'll have C. Then I'll have C. Well, I don't know what BY is. So I need to do some more trig. So let me say, look, BY is the adjacent to theta, right? That was what we called it. So we're going to use the cosine of theta because that has the adjacent. So the cosine of 20 degrees equals BY over 3. And if I do some algebra on that, I can get 3 times the cosine of 20 degrees equals BY. So BY equals, let me get my calculator. We've got 20 degrees again. 20 degrees I want to take now the cosine of that. Go up here. Cosine times 3. And I get 2.82. 2.82. Okay, by is 2.82. And it's pointing down, right? So I now know that C is the square root of 3.97 squared plus 2.82 squared, which is, so I've got 2.82, I'm going to square that, plus 3.97 squared equals, and then I take the square root and I get 6.28. 6.28. C is 6.28 long. Okay, so that's an important result for me. So let me make sure so that's the length of C. Add another page here. And now the question is, what's the angle? I need to know the direction of C. I need two pieces of information. So I need to know, let's call this not theta, but phi. Good old trigonometry angle designation, phi. A different Greek letter to represent a different angle. I've shown which angle I'm trying to get. And now we can label our lines. We're going to say that this side here, this is opposite phi, this is adjacent to phi, and this is hypotenuse of the new triangle. And the triangle, now we'll make a different color here, is like this. And so we're going to use our inverse trig again. What do we know? Well, we know the adjacent side, that is ABX. Here we know ABX. And we now know the hypotenuse. We know everything. We know all the sides. So we can choose any inverse trig function we want. So let's just do something a little different than we did last time. Let's do inverse sine. Inverse sine, and that's going to be opposite phi divided by hypotenuse equals phi. So phi will equal the inverse sine of the opposite of phi. Let's go up to the diagram and see what that is. The opposite of phi is this side right here. And since this box is a rectangle, this side over here is the same length, and that side is by. That's by. So we have by down here. We just have to keep looking back at the diagram. So this is by divided by the hypotenuse. And the hypotenuse was C, and we said C was 6.28. 6.28. In by, we have that from a different, here's by. There's by, 2.82. So we can rewrite our equation. And I would encourage you to keep rewriting stuff. Just make little changes from equation to equation. Don't make big jumps. Don't try and do it all in one step. So phi is the inverse sine of by, which is 2.82 divided by 6.28. And so we go to our calculator. Let's see. Let me see if I can find something that I want. Here, I'm going to use the 1 over button. The 1 over button, see, I've already got the 6.28 up here as my result. If I just take 1 over that, and then times 2.82 times 2.82, that's what I got to take the inverse sine of. And then I click the inverse sine here, and I get 26.7 degrees. Okay, so C as a vector is 6.28 units long, and it is 26.7 degrees. And if we look at the diagram, I have to give some kind of an indication of what that is. So I'm going to make a small little diagram here. This is C. This is 26.7 degrees. Down from the horizontal is 26.7 degrees. That's what we were looking for. We were looking for C. We wanted to know the length of the vector. So this is how we add vectors together. And not only add together, we've also learned now how to decompose a vector. So a vector that is not on axis can be broken up into two vectors that are on axis. And those two vectors that are perpendicular to each other are the components. So in the homework that you've got to do, you're going to have a bunch of problems that are going to require you to break things up into components. They'll give you a vector, they'll give you a context, so you can draw a diagram. I strongly encourage you to draw diagrams. Draw a diagram, and they're going to ask you for the components of various vectors. And pay attention to the units. Very important. Pay attention to the units. Some of the vectors are going to be distances, directions. And they're going to want you to break like a vector that points northeast. They're going to want the north component and the east component. There are some that are going to be velocities, and they're going to want you to break the velocity up into components. And the units will be meters per second or something like that. When you enter your answers in Math Excel, make sure that you correlate the units that the answer is asking for with the units in the question to make sure you're answering the right question in Math Excel. The numbers for the problems in Math Excel don't exactly correlate with the numbers in the homework. So the best way to keep yourself out of trouble is to make sure you look at the units and match the units. For instance, there'll be a question in the book that says, what are the x and y components of a vector velocity that's 20 feet per second and pointing 27 degrees up from horizontal? The Math Excel, that's all one question in the book. But in Math Excel, I'm going to ask you, what's the length of the vector? What's the horizontal component? What's the vertical component? Each of those will be a separate question. So there'll be like 3 questions for one in the book. There'll be 3 in Math Excel. So it can get confusing unless you make sure you keep looking at the units. As you look at the units, you should be able to figure out which question Math Excel is relating to in the book. Okay. Work on these. Again, I'll give you more time. I'll give you till midnight Tuesday to work on this. Sorry it took me so long to get this to you. Hopefully this is helpful. You can go back and look at it again to pick up some details if you need to. Thanks, everybody.